All right, so today I'm going to be explaining this important paper, this ICLR paper in 2022, and it's autoregressive diffusion models from Google Research. We introduce autoregressive diffusion models, a model class encompassing and generalizing order-agnostic autoregressive models. So you see, it is generalizing the order-agnostic autoregressive models and absorbing discrete diffusion, which we show are a special class of autoregressive diffusion models under mild assumptions. So they are simple to implement and easy to train. Unlike standard autoregressive models, they do not require causal masking of model representations and can be trained using an efficient objective similar to modern probabilistic diffusion models that scales favorably to high-dimensional data. At test time, ARDMs support parallel generation, which can be adapted to fit any given generation budget. We find that these autoregressive diffusion models require significantly fewer steps than discrete diffusion models to attain the same performance. So it's a variant of autoregressive models that is any order. We call it any order autoregressive, any order diffusion model. So ARDMs, they generalize the conventional autoregressive methods. When I say conventional autoregressive, the conventional autoregressive methods has order 1, 2, 3, 4. So it generalizes order agnostic. So you don't care about order, any permutation like 4, 2, 1, 3 can be done. So in contrast to standard ARMs, they impose no architectural constraint on neural networks used to predict the distribution parameters. So it requires significantly fewer steps than absorbing models to attain the same performance. Using dynamic programming approaches developed for diffusion models, ARDMs can be parallelized to generate multiple tokens simultaneously without a substantial reduction in performance. So you see here the generation of autoregressive diffusion models for generation order, for example, 3, 1, 2, 4. So the filled circles in the first and third layers represent effectively the input-output. So this is input and this is output. And the middle layer is just the internal activation. This is the hidden internal activation of the network. So for background, we just say usually we do the log likelihood of models that, for example, an autoregressive model can be factorized as a can factorize a multivariate distribution into just a product of the univariate distribution. That's why we like it, using just the chain rule. So if you use chain rule, you want to do maximize the log likelihood. So when we say x less than t, it means any time less than t. And they are trained by ensuring the neural network has a triangular dependency structure. For instance, implemented via causal modeling. Although this allows parallelizable computation of likelihood for all conditional distribution at once, to sample from the model, it requires the iterative sampling steps. Because first sample, but the second sample condition on the previous one, and so you need the iterative samples. So this is order agnostic, which is very good. Order agnostic autoregressive models generate variables just with a random order. No need for the conventional ordering, the default ordering, which is 1, 2, 3. No need for that. You can have any permutation like 4, 1, 3, 2, and so on. So everything is the same. It's just sigma, because depending on your permutation, it can be any time less than t. There is no need to be progressive. So this can be seen as a latent variable model, and the log likelihood, you just use Jensen inequality and that's it. Mind that hereafter we'll leave out sigma in our notation to avoid clutter. One approach to train is the procedure that is described for XLNet. It takes a permutation equivariant network like a transformer that is causally masked. Then inputs are permuted and outputs are permuted back according to a given order, which models the sequence in that specific order. However, such approaches typically suffer in likelihood score and cannot be combined with simple non-equivariant transformations. What is discrete diffusion? Discrete diffusion models define a destruction process on discrete data. For example, absorbing diffusion, for which each variable has a probability of decaying into an absorbing state. The opposite process to the destruction process is the learned generative process. The generative process models the distribution over variables that are currently absorbed and generates these with a probability. So the sampling is very simple. The input to algorithm is just f, and you just sample, because according to this permutation sigma, you create m, and then you update here like this. For optimization, we can use elbow loss. We can use elbow loss, and again here we have permutation, random time, because you can, for training you don't care about time, any time uniformly distributed from 1 to final time d. And so what is order agnostic autoregressive model? As I said, the main difficulty of parameterizing autoregressive model is the need to enforce triangular or causal dependence. Especially for 2D signals, this triangular dependence is difficult to enforce for arbitrary orders, and tedious design is needed for multi-scale architectures. To relax this requirement, we take inspiration from modern diffusion-based generative models. Using these insights, we derive an objective that is only optimized for a single step at a time. Starting at equation 2, a different objective for an order-agnostic ARM can be derived by replacing the summation over T by an expectation that is appropriately reweighted. So we can write the expected lower bound like this. So the term LLT represents likelihood component for step time t. We do not need to optimize for all LT terms. So for each data point, a single LT is optimized. Because as I said, we just sample from a uniform distribution from time t0 to final time t. So we desire parameterization for the model distribution for all sigma for any permutation at any time. So for any permutation at any time, it is in principle allowed to have entire new neural network. But look at that. If it would be very inconvenient because as the number of t grows as order of d, the number of permutation grows as order of d factorial, and this is not good because it can be any permutation. So this is implemented by masking variable at the input and predicting those at the output. To be precise, let x be the discrete variable. You have k classes and a neural network f and its output vectors, probability vectors. So conditioning is done by masking. For a given permutation, we compute the element-wise, which produces a Boolean mask. And the mask is then used by predicting f of mask element-wise product times your x. So for each location k, the log probability vector are used. However, given that these are important for practical implementation, they are specified in the following. The input to the function may be different depending on the data modality. For example, image and audio, the mask is applied to the input so that the values are 0 after feature normalization. The mask itself is also concatenated to the input as an input representation, which allows the model to identify whether a value is actually 0 or the value is in the absorbing state 0. For language, the input representation is augmented and absorbed values are instead set to a new class k plus 1. So we know a good property is that we can have multiple distribution over multiple variables. At the same time, you can do it. So we desire distribution, so we make the observation regarding connection between predicting future variables and then the likelihood terms. So it doesn't matter which step the model predicts. In expectation, all have the same associated likelihood. So parallelizing may incur some cost. As for a well-calibrated model, you have LT is less than equal to LT plus 1, but can be traded off for faster generation because fewer steps are used. In other words, the loss component are monotonically decreasing over t, and parallelizing a model incurs a cost, which the algorithm aims to minimize. Order-agnostic autoregressive diffusion models learn to generate variables in random order. We call it any order diffusion. So decisions on very detailed information are modeled relatively early in generative process. So we can structure the process into stages, where for each stage a refinement of the variable is generated. We refer to as upscaling. For example, instead of generating an entire 256 categorical variable at once, we can first generate the most significant bit and the subsequent bits in order of the significance. To define the process, it's helpful to first imagine the opposite process to upscaling, which is downscaling. So we define maps via transition matrices that define how a data variable downscales from its data value towards a common absorbing state. So if we have absorbing state, if you model as a one-hot x0, so from a diffusion perspective, upscaling is complementary to a downscaling destruction process, where each variable decays by zeroing its least significant bit. So depth upscaling is easiest demonstrated. So consider the task of generating a standard image with pixel values so that an image with d dimension can be represented by x8. So a downscaling by function that removes I least significant, we can define these transition matrices. So So you see in the figure bit upscaling matrices for data with 8 categories and hence 3 stages. So when we say S equal to 3, entries are white represent, so whenever you see white, it represents zeros, and colored represents ones. So it's now immediately clear how to parameterize the distribution. So we can do a direct parameterization. So in the example bit upscaling model, one model the else significant bits given the s-1 significant bits. The direct parameterization is generally more computationally efficient as it requires only distribution parameter outputs that are relevant for the current stage. This is especially useful when the number of classes is large. However, it can be somewhat tedious to figure out exactly which classes are relevant and should be modeled. The alternative approach is this data parameterization, which is similar to parameterization in that reference, Austin 2021. So in their appendix, they talked about the more details of depth upscaling is written, and the sampling from upscaling and optimization. What do you do for optimization? And the output is elbow loss. That they sample S as well. They sample time. They sample permutation. And finally, they can cover the loss.